So in this short lecture, I'm going to talk about surface micromachining and how it interfaces and works with design. Okay. So I'm going to cover a little bit about what MEMS design is in general and some considerations that you have to think about as a designer, like where you're going to make it, how it's going to get packaged, how it's going to be used. Those are things you have to think about as a designer. Okay, and then we'll talk a little bit about polymumps and surface micromachining in general. I'll have more detailed presentations later on that. So when you're a designer, you've got a plan. You know, what is it that I want to make and what does it have to do? And then how do I design something to make it get to that point? So on the right side, you can see a CAD drawing of a gear in a rack, right? The rack is a little spiky thing on the left here that the gear rolls in, right? So when this gear turns, this rack moves up and down. So this is what it looks like in CAD, and designers oftentimes, you know, do really good designs that don't work, right? So there's a disconnect. So things don't always work according to plan. For example, if you design something and it has a space, right? This tooth here and this tooth here has a space. Okay? If you design that space too small and you try to print it in the clean room, it ain't going to print. Okay? If you make that space too small, that gear will be fused into the rack. You think it'll turn? No, it'll be like it's welded to the rack, so nothing will turn. So you have to understand what the minimum space requirements are for the factory that's going to build it for you. Right? So that's called a design rule. Okay, so that you need to understand where this thing is going to be made. So when you design something, you go from concept to an actual product. And it takes a while to make these things in a clean room. Okay? It's a very simple design. It might take a month to get it through the clean room. At Sandia, it might take 6 months because they wait until they have enough designs to put on one mask set. The mask set costs $80,000, right? So you're going to maybe print 8 different designs on one mask set. So it takes a while to collect enough designs that you can, you know, make a series of parts for different people. And then once you get enough parts together to make the run cost effective, then it takes another 3 months or so to make them. And then you've got to release them, you've got to package them, you've got to test them. So it could easily be 9 months of a learning cycle. Right? So you submit a design, and by the time you get a part back to test it, to test your design out, it could be 9 months. And if you make a mistake as a designer, you just blew 9 months of time. Right? And you think if you do that a lot, you're going to be able to market anything? Yes, sir.
Will this MEMS Pro software allow you to rotate horizontally?
Yeah, you'll be able to do some 3D visualization with it and cross-sectional stuff. So you'll be able to cut across and see what the side view looks like. There's ways to do that. And you know, if you have a good simulation and software package, it'll show you what it should look like after you make it. The Sandia software was real good at that. I'm not sure about MEMS Pro. We'll have to see. So, you know, what are you making, right? Are you making something that's going to go into the body? Good luck getting that through FDA approval, right? That's really hard to do. Now, you can fast track it if you pick materials that have already been approved. So you can pretty much make anything you want and stick it in the body if it's encapsulated properly. And it won't fall apart. And if it's temporary, it's not that bad. Now, like the pill cam, you swallow the pill that has a camera in it, takes pictures of your GI tract. It's only inside you for a few hours. So getting that qualified by the FDA is a lot easier than if you're going to put a pacemaker in that's going to stay in for 10 years. Totally different set of rules. So, where is it going? So you've got to design your product so it's compatible wherever you're putting it. What kind of environment? Is it in space? Will it work in a vacuum? High radiation area? Are you pumping fluids into it? Right? MEMS are different than computer chips. Computer chips are easy. It's just electrical going in and out, right? And then you have photodetectors. So that's electrical and what? Light, right? Like the DMD chip that's projecting this image onto the screen, that's got moving parts in it, okay? But we're only letting light and electrical signals go in and out of that chip. So that's pretty easy. You can put a clear glass plate on the top, right? But if I'm making a microfluidic device, like a drug delivery system or a fluidic sensor or something like that, then it gets really messy, right? What are the fluids going to do to your gadget? Do you have to keep the fluids away from certain parts of your MEMS device? Okay. Are you going to do surface or bulk processing or both? So we're going to be designing just for surface micromachining with the polymumps process. But maybe if you guys want to go a little bit further, you can play around with some of the other opportunities that the software allows for and look at maybe a microfluidic device or something like that. What kind of shock conditions is it going to be under? Right? Is it going to work if you throw it against the wall? Does it need to work if you throw it against the wall? Usually MEMS are pretty good about this. They can take high Gs. That's why people like to use them. Again, is it in the vacuum? Is it in an atmosphere? Is it in a car engine? Is it in a gasoline environment? What kind of environment is it in? How does that interact with the materials you select? Is it a high humidity area? Is humidity going to cause stiction? So if you put humidity in contact with polycrystalline silicon, right, the water can collect on it, and it can actually cause it to stick. Because when you're talking about very, very small separations, small distances, if you get any fluid in between those surfaces, they can stick together. Okay, just think about taking two glass slides, maybe I'll bring them in one day, breathing on one, sticking the two glass slides together, you'll never get them apart. That's stiction, right? So how do you mitigate that? Are you going to make like 3 of these products, put them on a space shuttle, and then you're done? Or on the Mars platform? Well, then it's a little bit different, right? You can make 100 of them and test them, and test them, and test them, and test them, and then pick the best 3. Put them on the space shuttle. Right? The other 97 you can toss. But if you want to put them in cell phones, you don't want a 3% yield, right? You want 99.9% yield. You want them all to work. You want to make millions of them. Okay? Totally different design parameters then. You want to pick a process that's reliable and robust. Keep it as simple as possible so the thing will work. Get rid of all the bells and whistles if you don't need them. Okay, so there's different design criteria for that. And what's the best materials? Are you going to use polycrystalline silicon, or do you want to use something else? Do you need a metal part? Do you need it to reflect light? Do I need to coat it with gold at the end? If I do that, how am I going to do that? How are you going to release the parts? So what does releasing the parts mean? What do you think it means? To release the parts.
Chemical dissolvent.
Yeah, you use a chemical, right? When you're building these things, you're layering stuff on top of each other. Okay, so you might put a layer of a scaffold, sacrificial layer that provides a gap Then you put another layer that's going to be the part that moves. And then you put another layer that's going to be sacrificial again, to provide another gap. So when you put the next part on top of that, there's a space, right? You can't just layer the same material on top of each other because then they'll all stick together. Nothing will move. So you got to provide some space. Now you got to get rid of that sacrificial material, that scaffolding that created that space. So how are you going to release the part, right? That's tricky. You know, if you release it on the wafer and then you try to cut the wafer apart, you're going to destroy the parts. If you encapsulate everything on the wafer, cut the wafer apart, and then release it, then you've got all these little parts floating around in a bath, and you have to collect them and put them together somehow or mount them on something. So this is tricky too. So those are things to think about as a designer. So if you want to continue on with your education and actually become a MEMS designer, you probably need an engineering degree. Those are some of the details. Now, why do I teach design to technicians? Because when you're in the clean room and something doesn't work, you can see if it's a design problem or not. You'll be able to make that connection. It also helps you think about what the part, you know, how the part is made. So you have a better understanding how it's put together. So when you're working in the clean room, you can do better on your problem solving. And they do use technicians to do what's called chip finishing. So a designer and an engineer might draw out his design on a napkin and hand it to a technician and say, draw it up in CAD. Right? So you might have that opportunity. Some of our students have done that. Okay, so packaging is important. You have a lot of different inputs. Fluids and pressure, electrical signals, optical signals, vibration and shock. Those are all different kinds of environmental inputs. And then how many do you need? Is there a standard package you can use? That's really critical. If you can find a standard package to put your MEMS device in, you're going to save about a year's worth of work to get your product to commercialization. Packaging is not trivial. And some people even that are in packaging make tons of money because there's not a lot of people in that field. It's not simple. Then you have output, right? These are inputs to your product or to your device. You have outputs. It could be fluids again. You might bring 2 fluids in, mix it, spit something out, right? Separates things out. Again, electrical and optical signals can be coming in and out. So it's always best to talk to the packaging folks first when you're in the design phase. I used to know, and I still know a guy who used to work at Sandia. His name's Andy Oliver, and he used to work in the packaging side of the MEMS group. And he just would tell me crazy stories. He would get this design someone's been working on for like 2 years. And then they'd say, Andy, can you package this? And he looks at it and says, you know, if you would have just changed a couple of things, we'd have a standard package for it. You know, just a few things. I mean, they would have connections in the middle of the chip. So you'd have to put a wire from the middle of the chip over all this other stuff. You know how most packages are and most computer chips are? The packaging's on the edges of the chip, right? Especially in MEMS devices. The modern packages are flip chip. So you get an array of gold bumps on one side. Okay, and then they flip the chip upside down and they package it that way. But you know, the packaging guys know their stuff. So if you're starting from scratch, it's probably a good idea to try to figure out where this thing's going to go and how it's going to be packaged. And then the other question is where am I going to build it? Am I going to build it at Sandia? Am I going to build it at Global Foundries? Am I going to do it at Silex or IMT or MEMSCAP? Where am I going to make it? So if you pick the right factory that has the process you need, it can be relatively inexpensive. If you want to change the process, oh, I want to have another layer of this type of material in the middle. Or I want to make something thicker than they normally run. Then you're going to add a lot of cost because they've got to figure out how to do it, characterize it, and they might even need to buy a new machine to do what you want to do. And that can be very expensive for you. So always understand the process flow, and you will understand the PolyMEMS process flow, you know, within a few weeks, and you'll be designing to that because it keeps the cost down. And then if we actually make these things, you know, as a result of the design competition, it's not going to cost an arm and a leg, right? I mean, we can probably scrape up, you know, $5,000 or so to get them made, and then we have to get them released, and we can do that at the University of Utah or someplace, which would probably do it for very little
So
money.
if you submit a rudimentary design to somebody that's got a standard package that will fit in, I assume they're going to charge you a certain percentage of.
Yeah, but then you can package it yourself too, right? If it's a wire bond thing, you can actually buy the packages blank and then put your chip in it and hand wire bond it for your prototypes. And then you can put it in a circuit board and test it and do that kind of stuff. And once you are ready to go to production, there's a standard package that your part fits in. And then you would go to a professional packaging company that'll, you know, wire bond it automatically and stitch the parts together and all of that. And it won't cost them as much either because it's a standard process they have. Okay. So Sam built this a while back. I don't even remember what this was. Okay, so yeah, big consideration is try to use what's already out there, right? It's like if you designed a car and decided to use different kinds of gas. Now, how are you going to get the gas? How are you going to, you know, keep that supply going? Okay. So usually we do prototyping before we actually make it in the clean room. So rapid prototyping is a nice tool now that a lot of people use. Okay. The makers movement is big on this. We have a few examples in the back of the room from years past. The Ask Academy actually has a rapid prototyping tool. So we'll ask them to maybe print some of your designs later on. So if you make a lever, or a cantilever, or a gear system, or something like that, we'll see if they can print out a working model of it so you can see how it works. And nowadays, this is fairly cheap and fast. So if you have an idea and you say, well, I want to do something, and then it's going to flip up, how is it going to flip? Is something going to be in the way? And that's what we did here. It's kind of hard to see, but there's a planar gear, and then there's another planar gear that we popped up at right angles to it. This was a concept that one of my students, Eddie, came up with. He was thinking, how do I make a little car that can drive around, right? So you make a surface micromachine MEMS part, you pop up the wheels, and then flip it around, and the car can drive on the table. Really tiny car, right? So, you know, this is a proof of concept. How do I get a gear to flip up and do that? So here's his design on the lower left, and that's what he ended up with up on the upper right. So overall, the design process is pretty straightforward. There's a lot of details in each one of these steps. But your initial design might be on a napkin, and then you'll transfer it to a CAD drawing. Then you'll look at it in CAD, and you'll look at 2D visualization. So this is a cross-sectional view. So you take a slice across the part that you're interested in looking at and see if it looks the way you think it will look. Okay, then you can do a 3D visualization of it. Look at it in 3D. Then there's something called finite element analysis. And think software like ANSYS and SolidWorks. So you can create a working model of it in virtual space and then turn the gear and see how the other things respond to it. Okay? I don't think we're going to do much of that this semester. It's probably more than we can handle. And then once we think we got a working part, or what will be a working part, then we do design rule checking. And we do that usually throughout the whole process. So design rule checking, you want to make sure that you're not breaking any of the process rules. So what do you think is important when you're designing? What kind of rules do you think we have to adhere to? Any ideas?
First thing, will it survive all the environmental variables it's going to be exposed?
Okay, but that's not really part of the design rule checking. Design rule checking is all about, did I design something that I can't build? So, clearances, exactly, right? So, back to the original description of the gear and the rack. If I design that and I make the space between the gear teeth and the rack teeth too small, when I send it to the factory to be built, they're not going to be able to pattern that, right? There won't be a gap. Once they do the photolithography, develop and etch, you know, you might have some places where the things are fused because you didn't adhere to the minimum design rule space, right? Sometimes it's half a micron. Usually it's 1 micron. I think in polymumps it's 2 microns. So you got to have everything 2 microns apart. You can't make a line thinner than 2 microns because they can't pattern it and etch it. Okay, so if you're going to make a spring and you decide, oh, 1 micron will be perfect, and it's like, no, you can't make a 1 micron spring. It has to be 2 microns. So what do you change in your design so your spring will work? So the design rule checker looks for minimum CDs, minimum critical dimensions. That's one thing it looks for. Okay? So is there enough tolerances? That's a good term, tolerances. The other thing it looks at is what? You're going to align things, right? One layer you're going to align to the other. Remember when we did the backside alignment? We couldn't see half of the wafer, right? You can only see 1 mark, not 2. And remember how it ended up? Right? They were misaligned. Half the wafer was misaligned. Okay? So alignment's the other thing. So if you say, yeah, they got to be perfectly aligned. Well, nothing's perfect. So how much tolerance do I have? And then if I'm misaligned by, you know, let's say alignment tolerances are plus or minus half a micron. Okay. Well, what happens if I'm off half a micron? Will the product still work? Will the gear still spin? Or is it going to wobble? Or is, you know? So you get the idea. So this design rule checking is real important because you don't want to create a design that's not going to work, that can't be made. Okay? And then once you do all that checking, then you can go ahead and try to make the part. Now this is a little historical slide from Sandia National Labs that I like to show. They went through a series of evolutionary steps in their process. So the first time they made a MEMS device, and the first time anyone made a MEMS device, a surface micromachine device, they used 2 layers. So that's all you need. Okay, so they have a ground plane, right? You can't just make something that's conductive and put it on top of an insulator. It just doesn't work. So they made a ground plane, and then they made another structural layer on top of it that can move. These long skinny things you see here, okay, these guys here, those are springs. This is a comb drive, this is a comb drive. You can see that this will oscillate back and forth from left to right. Okay, so if you change the voltage on these other combs, you can get this thing to repel and attract, right? Depending how you set the voltages and the signals. And you can get the thing to oscillate back and forth. And if you drive it at the resonant frequency of the mechanical system, right, you won't need much energy. That's the high Q point where you get the maximum transfer of energy to the vibrating system.
What's the generic name for the layer above the ground?
It's poly 1. first layer, poly. This one's poly 0. It's the bottom layer, doesn't move. Okay? These are all examples of polycrystalline system, surface micromachine type stuff. Now there's a lot of other processes in MEMS, but we're going to focus on the surface micromachining stuff. Okay? So this is a resonator, a very, very simple device. And they designed this so they could test and do calculations. You know, is my spring constant what I think it is? Right? The way you figure that out is drive it at resonance, find out what the resonant frequency is, and then you can back calculate what K is, right? The spring constant. How does that compare to the model and the simulations? And then once you learn that, then you can build more complex designs. Because springs are a big deal. Then if you have a third layer, you can do things like hubs and pin joints. Things can spin. If you add a fourth layer, you can do even more. Okay? And a fifth layer, you can make very, very complex systems. I think we're going to be on the 3 or 4 layer process. Okay? These actually, this has 1 layer that moves, this has 2 layers that move, this has 3 layers that move. I think polymumps is here. And the Sandia Summit 5 has 4 moving layers. But they used 5 because everybody else said, hey, if I have 1 moving layer, that's 2 layers. Okay. So that's how it came to play. And here you can see the cross-sectional views of some of the complex things you can do. So you can do some kind of spinny parts if you have two moving layers, right? You have a hub, and then you have something that can spin around it. And you'll do that in the class. You'll make some of these things. Okay? So these are labeled polysilicon level 1, poly 1, poly 2, poly 1, 2, 3, poly 1, 2, 3, 4. Okay, those are the moving parts. And poly 0 is the ground plane. You always want to put something underneath to keep the charge from building up. Because what's underneath the poly 0 is typically silicon nitride.
So Summit 5 was just constant 5 level.
Mm-hmm. Yeah, they developed this in the mid-90s. So they've been making parts based on that process for quite some time. It came out of, I think the first parts were out of DARPA. And I think they were related to the historical MEMS cap. DARPA started making some parts and trying to see, can I make very small mechanical parts? And they were doing that back in the 70s and 80s. And then it moved to Berkeley and Stanford. Right? So they started making MEMS. And then University of Michigan has a big history of MEMS. In fact, I've got 2 historical books with pictures from all the different products they made at University of Michigan. I'll bring them down here and you guys can flip through it and get ideas and see stuff. They said we could use that resource as well. In fact, Andy Oliver got me those 2 books. So I'll probably bring that in. I wish they had it on a PDF. Yeah. Because there's some cool stuff there. I should ask permission to see if we can scan it in. But anyway, there's University of Michigan was one of the first universities, along with Berkeley and Stanford, that were making MEMS parts. And they did mostly surface micromachining in the beginning. And there's some really cool images that you can find online. All right, so what is it that we do to make these parts, and why do we do surface micromachining? Okay, so we like to use surface micromachining because we use the same equipment as making computer chips. And MEMS can't be really, really small, can they? If you make them too small, they won't work. Right? You want to move stuff and you want to sense things. So you need a certain amount of area to do that. So you can make MEMS devices where the smallest part of it is 1 micron. The smallest space, the smallest spring width is a micron. Most of the time it's bigger than that. Well, we're making stuff on computer chips that's 0.1 micron or 0.04 micron resolution. We're using $40 million photolithography tools to do that. So we don't need all of the old equipment. So the old equipment's floating around and you can buy them for cheap. MEMS people love that, right? Because they're all startup companies and small volume, and so they use older equipment, and they can use the older semiconductor equipment to do this stuff. Most MEMS companies produce things on 6-inch wafers instead of 8-inch. Most semiconductors are doing 8-inch, and then the really big ones, like the Intels and the AMDs and the global foundries, are doing 12-inch wafers. But that's real high volume. Then you can justify the equipment cost. But if you have a medium or low volume, you're going to do 6- and 8-inch wafers. So, taking a look at this graphic, we start by growing wafers, right? You guys are already familiar with that. We grow crystalline silicon wafers, and we put a thin film on it, right? And then we pattern the thin film with photoresist and photolithography, kind of like what you did with the tourist wafer. And for those of you who did the pressure sensor, we did a lot of that, right? Nothing new there. And then you etch it. So whatever's showing after the photoresist is applied and patterned, whatever's showing gets etched away. Then you strip the photoresist and then you do it again. And you keep going in this circle and build up layers and layers. And at every layer you have a photomask. Okay? So at every layer you have a photomask. Okay? So what does the designer control in this whole thing? Or does he control anything?
Mask set, maybe?
Yeah. He makes the masks. That's what the designer does. So he makes the designs, he makes the masks, and then sends his design to a mask shop. They make photo masks. They take his design, they put it on chrome and glass, usually. Right? If it's Liga, it's what? Gold and beryllium. But they'll make chrome and glass sets, and there's a set for each layer, each design layer. So as a designer, you're gonna draw things in different layers, and then the layers are going to combine and make a product. So he controls the mask set, he or she. And so it's important that you understand how the masks interact with the process, right? Because a lot of times we'll make a mask, we'll draw a 1 micron line on it, but when I print it in photolithography, it's 0.9 microns wide to get the best resolution, right? To get the best line. And that's called a bias. So there's a change from the design to the actual printing, and it's called a bias. And then you have another bias that happens when you etch that in the etch group. So that 1 micron that's on the mask might be 0.9 microns on the photoresist, but then after etch it might be bigger because you don't have a straight profile. You might have a trapezoidal profile. So the bottom of the line could grow 0.2 or 0.3 of a micron. Okay, and then the question is, well, what's important, the bottom or the top or the average for that part of the device? So as a designer, it's good to understand these weird nuances, right? Now, a lot of times a designer doesn't care. He draws it the way he wants it after etch. And then it's the job, he sends his design to the factory. The factory's job is to offset everything to compensate for the process biases. So he sends a mask set that's exactly what he wants after the etch. So if he draws it 1 micron, he wants 1 micron after etch. So the photolithography guy knows the difference between mask and printing, and he knows also, because he talks to the etch people, the difference between lithography and etch. And he goes, okay, I got to add 2. So then everything that's a micron on the mask for that layer is going to be 1.2 micron drawn on the mask because he's losing 2/10 in the process. So we did a lot of that at TI when I was there. You know, I had to know what that offset was. Okay? And it was really hard sometimes to explain that to the designers. You know, because let's say they draw something that's 1 micron, and then they put a 1 micron space, and then they draw something that's 1 micron, right? Because the minimum space is a micron, and the minimum width is a micron. But if I have to add 2/10, because I'm going to lose 2/10 in the process, now my space is 8/10 of a micron. If I have two lines too close together, they won't image right. They'll be fused. So we have to give them pitch. Say you can't have a pitch that's closer than a certain amount. And pitch is the difference between one point in a structure and the same point in the next structure over. That's pitch. And then you have width, critical dimension, and critical dimension here. And those two add up to the pitch. So if this gets bigger, this gets smaller, right? So we'll talk more about that as we go through. But you can see there's a lot of complexity and a lot of detail that you have to be aware of. And, you know, as a technician, you might just be working in thin film, okay? But at least you'll know that if I make my film a little too thick and I'm making a MEMS device, then that spring is going to be a little stiffer because it's thicker. So now my resonators won't work. So then you'll understand, gee, I have to really maintain thickness control. So you get the idea, right? There's reasons why we have to do these things. So what materials do we use? Well, with surface micromachining, we have structural materials, okay? And those films have desirable mechanical and electrical properties. They're usually low stress. So what does low stress mean? Or let's put it another way. What happens if we have a high stressed material and we release it? If you hold something down that's stressed, right, you can keep it nice and flat. If I let go, it's worked. So if you don't have low stress mechanical materials, structural films, you release it and those cantilevers will bend. The mirrors you're trying to make will be warped. They'll look like potato chips. Okay? So you got to have low stress materials, and that was a big issue when they started making polycrystalline structures, because in the old days when we did polycrystalline for computer chips, they were all glued down basically, right? The stress didn't matter as much. But now if you make a little part and release it, it's going to bend. Okay, then so we have structural materials. Those are the things that are going to stay behind and be moving and be the parts that do the work, right? And then you have these sacrificial films that go in between the structural layers to give you that space you need, so you get those clearances in the z-axis. Okay, so both films have to be compatible in the fabrication environment. So if you're making these in the same kind of fab that you're making computer chips in, you know, you don't want them conflicting. You don't want to cross-contaminate. You don't want to have problems that way. So polymumps, the structural materials are polycrystalline silicon. They also have a metal layer that we can play with, which is kind of neat. And then what they use for sacrificial material is silicon dioxide. So we can dissolve that in what? We did that. We made our tourist wafers. HF. We use hydrofluoric acid to get rid of the silicon dioxide that's between these layers. We also use silicon nitride as the electrical isolation layer. That's the first layer that goes down before the poly zero. So that's to isolate electrically from the parts and the wafer itself. And then we build on top of the single crystalline silicon wafer. Okay, so that's our substrate. That's what everything is mounted to. So here you can see we've put down a layer of sacrificial thin film. That's the cross-hatched white-looking material here. And we have a structural thin film. That's the blue one. So that could be polycrystalline silicon or metal. Then we pattern and etch the structural layer. And then we start to wet etch the material underneath it. And if we don't leave it in the etchant long enough, you know, we're going to leave some material behind. And sometimes this is intended. Okay? You don't want to etch it all away. So you have these little cantilevers hanging out here on the sides. Okay? So this is an example of a single level mechanical structure with an unpatterned sacrificial layer. Now if I wanted to attach this blue piece to the substrate, what would I have to do to attach it? What do you think?
Deposit another layer on top of it, could you?
Well, how am I going to attach this to this? You got this thing in the middle, this layer. What do you think I have to do? What if I have a hole in there? I make a hole in the cross-hatched area. Okay, if I make a hole in it, and then when I put down the thin film, it's going to fill the hole, right? And connect the two. And then if I get rid of all of this, you'll have it attached. It's called an anchor, right? So that's the kind of things you have to think about. Okay? So we're going to go through a very simple process. Very simple process. We start with a single crystalline silicon wafer. We put something down, say a sacrificial oxide in this case. I'm going to kind of duplicate the last slide. Okay, so I want to pattern that. So I'm going to make a hole in it. So I put some photoresist on there. That's the red stuff. Then the mask is this shiny thing that's hovering in space virtually. Has a hole in it. So the light goes through the hole, right? Hits the photoresist. Where the light hits the photoresist, there's a reaction, right? It's got a photoactive compound. Photoresist turns into an acid, usually. Use positive photoresist. Most work that way. So it becomes slightly acidic. And then we develop it in a base. So where the light hit gets dissolved away. So now you can see the red layer has a hole in it. The red layer is a photoresist. The hole shows the, what's the green stuff? Do you remember?
It's the oxide.
Yeah, it's the silicon oxide. So that's exposed now. So if I put this in HF, what's going to etch? The stuff that's exposed, right? So the silicon dioxide that's exposed in the hole in the photoresist gets etched away, and that's what the next figure in this slide is showing you. So the stuff that's not protected gets etched away. Okay? So that's pretty cool. So now we got a hole in our oxide. We take the photoresist off, still have a hole in the oxide. Now we put our structural layer on top of that, which in this case is polysilicon. And we call it poly for short. It's not a polymer. I was thinking it was a polymer for like my first year or two at Texas Instruments. It's polycrystalline silicon. I didn't know. I had never been trained, so no one explained it to me, and I was not smart enough to ask what kind of material it is. So polycrystalline silicon, we deposit that, and it's conformal, right? So you see a little bit of a dimple there where it's filled in the hole. Okay, so now you can see it created a bump too, right? And then we cover that with photoresist, and we're going to image something on it, in this case the Sandia Thunderbird. So you can see where the light goes through and where the shadow is projected. So everything that has light on it is going to get developed away, right? So now this upper left slide or picture shows the photoresist image on top of the, what is that blue stuff? The blue layer was what? Polysilicon, right? So we're going to protect where the photoresist is, so everything else will get etched away, and that's what the next part's depicted, right? After you etch the polycrystalline silicon, you still have photoresist on top, and we have to get rid of that. All right, so we strip the resist off, and now we've got a Thunderbird that's been anchored through the silicon dioxide, right? So it's sitting on top of the silicon dioxide except where the anchor is. Okay? Then what do? Then we get rid of the sacrificial layer. And now our Thunderbird can flap its wings, right? It can bend. Can't spin. We didn't make a hub or anything. It's pretty limited. But at least it can flap its wings, right?
So is the polysilicon etched with BOE just like the silicon dioxide?
No, polycrystalline silicon is etched with RIE. It's a reactive ion etch. I think our fab, our MTTC, can deposit polycrystalline silicon.
How is it etched away if it's underneath the structure?
Well, that's the silicon dioxide that gets etched away, and that's done with liquid. It's a diffusion process. Now, if this is really as big as we drew it, right, so we'd have to put release holes in here, right?
Polycrystalline silicon is the structural layer.
Yes.
Okay.
Yes, the polycrystalline silicon is the structural layer, and the silicon dioxide is the sacrificial layer because it gets sacrificed. It's the scaffold. So, how many masks did we use in this? 2. What were they for?
One was for the anchor hole, and the other was the bird.
Okay. How many etches did we do?
First hole, you had to etch away the photoresist and the Thunderbird. You had to etch away, when we were all done, we had to take the thing up from underneath. 3. There's always one.
So we etched the pattern of the hole, right? And then we etch the structural layer. So we have 2 etches, and you make a good point, right? We do have the release etch, so there's 3. There's 3 etches, 2 mask layers, 3 etches. And some people, like you alluded to, consider photoresist strip as a type of etch. Usually in semiconductors and stuff, they don't look at strip as an etch. Strip is done as a cleaning process, right? So people don't think of it as an etch. But in an effect, it is an etch of sorts, right? You're removing material, so that's a definition of etching. I'm removing material. So you can include those 2. So we got 5, depending how you define it. Okay, how many depositions?
But isn't like developing different than etching?
Oh, yeah.
Developing a pattern is not the same as etching.
Yes, you're right. But some people would consider that removing material. So you could count that as a type of etch. But in industry, they don't call it etching.
Yeah, it's developing.
It's developing, right? So we call that develop. We call taking the resist off of the material strip, or resist strip, okay? Or ashing. There's another way we can do it. We can put it into an asher, which is basically a really basic reactive ion etcher of sorts, right? You have radio frequency, you heat up some gases in it, and it's usually oxygen, right? Oxygen will react with organics really well, and so you can ash the photoresist, which is a type of organic, has a lot of organics in it. It's a It's a polymer with a lot of carbon in it, right? So you know, that's, ashing is not considered an etch per se in industry. But if you were to define it that way, you know, the concept is you're removing material. So how many depositions? Well, material depositions, how many did we have of the ones that we care about? Yeah, the structural and the sacrificial, right? But some people might say, well, you're depositing photoresist, so that's a type of deposition. So, you know, I wouldn't argue the point, but as long as you understand, you know, you got 2 mask layers, but there's a lot of other stuff going on. There's several etches, several depositions involved just to make those 2 layers. Okay? So the question there is, will it move? So if we go back to the Thunderbird, will this move? Well, maybe up and down on its own, but it really won't move at all, right? Because we don't have a way to make it move. If we had like an electrical plate here, and put a positive voltage, and then this was grounded, then the negative electrons would go towards the positive, and then you have negative and positive, they'd attract, and you can get the wing to bend. And then you let go of the voltage, and the wing would pop back up because of the spring constant of the structural material. So you have to put something else in there to actuate it, right? So in that case, it would be a little bit of a plate or something underneath the wing. So if we did that, then we'd need another layer, right, and another mask and another set of etching processes and deposition processes, right, to make it move. It can't spin because we've anchored it to the ground. So to make it spin, we'd need a hub so it doesn't fall off. So you anchor the hub, right, and then you have the Thunderbird with a hole in it that's around the hub. The hole's around the hub. So then it can spin, but it won't fall off. It's like a bearing. Okay? So you'll learn that too. Now we can get pretty complicated. Here are some examples from Sandia. Okay, so the bottom left picture, scanning electron microscope picture, you see this flexure here and this flexure here. Then if you go to the go up one from the bottom left picture, you can see the flexure further away. So you can see one of them goes up and down, and the other goes left and right. And if you do it right, you can get this little gear here to spin, or this gear. It's another picture of the same gear. You can get that gear to spin. It's attached at the pin joint right here, at the point right there. Okay, we should make one and try to get you guys to make it spin by you going this way, back and forth, and Ramon going the other way, and see if you can get in sync to make it go in a circle. Not easy, but you can do that. 2 linear motions, you can combine them and make it go in a circle. You guys ever use oscilloscopes? Ever do Lissajous figures? You put one frequency in for Y and you get the sine wave. Then you put another frequency in for X. If the frequencies match, right, you get an oval or a circle depending on the relative amplitudes of the 2 signals, right, the voltages on them, right? And if they're slightly out of frequency, then you'll see this thing. It'll look like a ring oscillating on the screen. And if one frequency is twice of the other, you get a figure 8. If it's 3 times, you get 3 lobes. Okay? So that's by changing the input frequency in X and Y of your electron beam that's inside the cathode ray tube. Same concept here, right? We have one frequency in one leg, another frequency in another, and if you sync it up just right, it'll go in a circle. Okay, so you can make linear motion go in a circle. So, you know, that was a big deal. How do I get an actuator that moves left and right to make something go around? Okay, so it took Sandia a while to come up with that comb drive system. So they have 2 comb drives. You can see parts of them in this picture. Okay, so but this requires quite a few layers.
Comb drives are just moving the spring back and forth.
Yeah, it's moving the flexure in one direction. And the flexure can bend a little, so that's how you can get it to go in a circle, right? Because they flex. Now, if you look at this pin joint system where it connects to the gear, that's what's in the bottom right corner. You can see how complex that is, right? So you want this thing to be able to spin. So here's your pin joint here, and it's free to rotate. So as this gear goes around and round, that pin joint isn't locked in, right? It can rotate, but it's not going to fall off of the gear, because if you look underneath, it's wider, right? It can't come out of the hole. It's like a rivet, right? A rivet you put in, and then you make the back a little bit bigger, and the front's a little bit bigger, but the rivet can spin. Some rivets, right? So you can see you can get quite complicated if you have enough layers. Oh, let me go back one slide. There's something cool here. So this thing can run at 350,000 RPMs. Which is pretty good. And they can do 10 to the 9th revolutions before it breaks apart. Okay? So millions of start and stop cycles. Eventually they do fall apart, because polycrystalline silicon is a polycrystal. It has grains, and occasionally a grain will loosen up and tumble around inside of there. So it's like throwing a rock inside of the washing machine. It'll eventually break, right? So, so it doesn't last forever. Okay? So they've got better systems now to make rotary motion, but this is one of the first ones, and kind of neat to go through that. So, in summary, designers are confronted with a large list of details, things like design rules and what are the limitations of the process. Usually that's folded into the design rules. Packaging concerns. What about interfacing? We have liquids, gases, light, electrical connections that we have to worry about. Okay, modeling. Or do we have the right model? Right? If I model this on a computer, is it telling me the truth? Right? Or is it all fiction? When I build it, it won't work. Okay, and of course, teamwork is really important, because one person can't do it all. Right? So you might be designing like a small part of a whole MEMS device. So you got to talk to the other designers. The design team has to talk to the fabrication team. Hey, will this work? Can I make a 0.2 micron space? No. How can we make a 0.2 micron space? Oh, well, we can deposit really thin films. So if you want to make a 0.2 micron space, we can play games with deposition. We don't have to do lithography. Then you start going down that path. Okay? You never want to throw anything over the wall and say, okay, packaging guy, now it's your problem. Right? You'll just say, yeah, I can do it. Give me $2 million in 6 years, and I'll make a new package for you. Or you could redesign it in 20 days, and it'll fit in this other package if you move these 2 parts around. Right? Let's see. If you make a mistake in design, it can cost a lot of money. Because by the time you get your parts back and they don't work, you just lost, what the example we used was, 9 months? You lost 9 months of product sales, because you only have a limited amount of time that you can sell a new product, and then something else takes over. Okay, so how long did the S3 last on the market before the S4 came out and the S5? And I mean, I bought this phone, a year ago? Maybe a year ago? Might have been a year or 2 years ago. It's not that long, and they're already on the 5. So they're doing more than one a year. We're talking 6 to 9 months for each design revolution. So it's got to be fast. Okay?
Comment, the students that were given the testimonials for AP honors things last night.
Mm-hmm.
This one kid said that what he learned from taking AP classes, it just raised the bar for him to do his own self-checking. of course, in physics, you're always being very precise and stuff. But this whole thing, he used an example, he said that he was at this one job, but they stopped giving jobs to this one guy because he made so many mistakes that they just had to redo everything he did anyway. So they, by, having your own analytical skills, you basically can check yourself, and then you become very valuable because you don't waste time, you don't waste product.
And if you can recognize what you don't know, and you can ask another person to look over something, that's valuable too, right? You have to recognize the limits of your skills, and then you learn from that. So I used to talk to people all the time at TI and at Philips, and we'd have lunch discussions about processing issues and that kind of thing, and basically brainstorm and come up with new ways of solving problems. So, but that's a good point. The more you practice at critical thinking and problem solving, the better you get at it. The more you practice at presentations, the better you get at it. The more you practice at doing job interviews, the better you get at it. So, and you have to reflect. Every time you do it, reflect. What went well? What didn't go well? Okay, what can I tweak so the next time it's a little better? So that's the continuous process.
If you're not paying attention, you make simple math errors, and if you're really good at math, you just don't make those errors.
And that comes through practice and focus, yeah.